So that makes me feel better.
I understand too.
Yeah, I feel comfortable.
Good?
Yeah,
Fingers
feel
crossed.
All right, let's get started. Any other homework?
Am I in the way?
Again. This is the end of it right here.
Shane, you were never in the way.
Chapter 3. This is where you possibly could start losing some people. So I don't know what I got to do to give that extra attention to detail here, but I'm going to try to explain it in a way where everybody's going to get it, but it gets confusing a little. I'm trying to think. Let's talk about these terms. I don't know what I'm talking about. Let's just jump to something. Blah, blah, blah. Yeah, okay. All right, let's go right here. Remember this problem from way back? We found our feasible region. We had 5 extreme points. We found that one, I think, was the optimal solution right here. And this line was when we took the objective function and we kept moving it out, moving it out, moving it out until we figured out the very last spot it was going to touch. It was down to these two. That line's the objective function. Well, if the objective function numbers, which are right here, if that 5 or that 7 were to be slightly different, it may or may not change the optimal solution. And every time you change one of these numbers, the slope of this objective function line shifts a little. And there's a little bit of shifting that could go on either end with either one of these numbers, and that is still the optimal solution. The amount that these numbers can change and the optimal solution doesn't change is called the range of optimality. The word optimality is where everybody starts to go, wait a minute, what's that refer to? This is referring to the numbers in the objective function. That's what I would write in my notes. Optimality is always related to the objective function numbers. Right? The word feasibility is always referring to the constraint right-hand side numbers. Everybody hear that? The word feasibility is always referring to a constraint's right-hand side number. Like on this one, it says less than equal to 8. On this one, it says less than equal to 19. That 19 and that 8 are all about the range of feasibility. So we're getting into optimality and feasibility here with a couple of names of things we're going to learn. But the key is, to not get these confused, is to have the word optimality somewhere in your notes that say, have to do with the objective function. Numbers. And then the feasibility, put on there, right-hand side of constraints. That's what it is referring to. Now that we know that, come on. Hang on. Here we go. Boom, 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 boom. Hang on. Wow. Look at all the stuff we're skipping. What happened? Is there absolutely no output on this? Okay. You ready? This is the top half of an old output. Here's the bottom half. What I want you to notice on the bottom half is objective coefficient ranges. On this particular software, it labels it objective coefficient ranges. It's another word for range of optimality, because the coefficients are the numbers in the objective function. And that section is giving you the ranges of optimality, which means the range in which those numbers could change up or down, and the optimal solution is still valid. For example, if we go back and find the objective function for this problem, the current values with the variables x1 and x2 are 6 and 9. I don't know if this is a max or a min. We'll get to that in a minute, but I know that the objective function says 6x1 plus or minus, probably a plus, 9x2, but I don't know if it's a min or a max right now. Now, here's what happens in real life. Let's say these represent profit contribution for 2 products. In real life, I've had experience where I've done all this research to find the profit contribution of a product or a thing. And someone comes to my office and say, hey, remember that meeting we had last week where we're trying to figure out the cost of every little thing if we go on with this new product, and you're figuring out what then would be the retail and what our gross margin would be, and then we took labor and figured out how long it takes by making a couple and da-da-da-da. To get to this number right here, well, I made a mistake. When I had the conversation with the supplier, they said for sure it was gonna be $3 per blankety blank, whatever the units are. But now they said they misunderstood me, that really is $3.50 per unit. And because of that, our profit margins are going, this one's going from 6 to 5. Let's just say that's the only one changing right now. That one's going from $6 per unit we make and sell to $5. We already scheduled, we already made a decision that we're gonna buy or do something 1.5 and 2. That's our optimal solution. Should we be stopping all of production right now because we're doing the wrong thing because of this miscommunication on this cost? And you're shaking your head, no, why?
Because it's, as long as it's between 0 and 12, it's fine. So if it went down to 5.
If it's the only change being made, yes, exactly. Everybody hear that? This is going from 6, what did I say, to 550? Or 5? 5. This is going down to $5. Do not stop that line. The cost involved in stopping whatever's going on, pretend, hypothetically, is too much. Let's look and see what the cost involved is. If that's going from 6 to 5, the optimal solution is still valid. Which means, if this were a graph, again, that change the angle, change the angle of the objective function line, probably a shift this way or shift that way, but not enough to where this still would be the optimal solution when we were to regraph it and move it out again. So because of that, we can make a quick decision. Optimal solution is still valid. Don't make any changes. Everybody stay with the production schedule we planned on, or whatever the situation may be that we have to make a decision. Now, let's take it a step farther. We just found out from our supplier, where is that? Right here? That actually the price we were quoted for the raw material is going to be less than what they thought it was because of the miscommunication. And that our profit is going up on that particular product. Instead of a profit contribution of $6 per unit, it's going to be like $7 per unit. Is the optimal solution changing? I would see no. Because the increase of $1, which takes it to 7, is within the upper limit. Everybody's with me. This is real easy right now, right? Product number 2, same deal. As long as the change of whatever that number represents in the objective function stays between $4.50 or 4.5, whatever it represents, and there's no upper limit, then the optimal solution is still valid in that case also. Those numbers on how far it could go up and down is the range of optimality. Stay right there. You ready? Whoops. Right here. This part. This particular software says right-hand side ranges. Some softwares will label it range of feasibility. Same thing. When you see the current value, there's this particular problem, linear programming problem, has 3 constraints. I can tell by looking at the output. And I can tell the current right-hand side of each one of these constraints are 8, 30, and 2. Maybe less than equal, maybe greater than equal, but 8, 30, and 2. These are limitations. They usually represent things like there's only so many hours available in this particular department. The paint department is usually the case. Or it could represent a limitation on raw material. We had 8 tons of aluminum is what we were expecting from our supplier, so we went ahead and scheduled everything based on 8 tons showing up, and we only had 7 tons show up. We're short a ton of raw material here. The ranges in which these could go up or down to, this is all telling you whether or not, these dual prices are valid or not valid. I want to make sure you hear that again. The right-hand side of constraints have a range they could go up or down to individually, and if they stay in that range, then that means that these dual prices are still valid. Even if you don't know what these dual prices mean yet, it's all about whether these are still valid or not when a change takes place. And that range of feasibility, it's all about that dual price, whether those are still valid. You ready? The dual price is telling you the effect the right-hand side of a constraint will have on the objective function value if it changes for 1 unit up. Let me say that again. If the right-hand side of a constraint changes 1 unit up, increases 1 unit, this is the effect it will have on your objective function value. So let's look at constraint 2. If it increases by 1 unit, as long as it's within its upper range, that's still valid. Now that I know that's valid, the supplier called me and said, I have 1 more ton of aluminum. Let's pretend that's the aluminum. And it's within our upper limit. We can make a quick decision because that supplier wants to know the truck is in your area. I know we dropped off your week's supply, but the truck's in your area. We got an extra ton. I'm offering it to you right now for 50 cents a ton. Right? Do we take it? It says here, for every additional unit that particular constraint, right-hand side goes up, it's going to have a negative effect on our objective function value. No matter if it's a minimize or maximize, it's going to have a negative effect. That's what that means. Positive or negative effect. This is where I start losing people. You have to determine whether it would be this going up or down based on what a negative effect means. If this is a max problem, we're trying to maximize this, maybe it's profit. What's a negative effect? That goes up or down. So you would subtract. But if this is a minimized problem, if this represents our minimum cost that we can get it down to, what would be a negative effect if this right-hand side goes up? You would have to add it. Even though it says negative, you got to know to add it because you're going to go, oh wait, negative effect. I don't know whether you add or subtract yet until you go back and see whether this is a minimize or maximize. Let me say that again. You're looking at the right-hand side of a constraint. Let's do constraint 2. You ready? The right-hand side of constraint 2 is 30. It's going up to 31. So as you're answering this problem, you're going, a 1 unit increase is within the upper limit. So the dual price is still valid. Now you go to the dual price. Since the dual price is a negative effect of 60 cents, and this is a maximization problem, hypothetically, you then show, you're going to say, because it's a maximization problem, it's got to have a negative effect, so you're going to subtract 60 cents from that. The new objective function value would be $26.40. Got it? But you would be writing, the right-hand side is going up 1 unit. It's within the upper limit. It's going to have a negative effect of 60 cents on the objective function value. This is a minimization problem. You're writing, this is a minimization problem, so I'm adding 60 cents. $27 plus 60 cents. Our new objective function value is $27.60. It went up because it was a minimized problem, and the negative effect would increase that. That's why we added it that time. Are you ready? Our right-hand side is 30 currently, and we have the opportunity to get 3 extra units. 3 more units. Let's take a look. Is our dual price still valid? This is constraint 2, currently at 30. We got 3 more units. No, the camera can't see all your head shaking. Someone say yes or no.
Yes.
Very good. Yes, because 30 plus 3 is 33, is within the upper limit. Dual price is still valid. Let's check what effect it's going to have. It's going to have a negative effect of 60 cents per unit of change. There's 3 of them. 3 times 60 cents is $1.80. This is a minimization problem. Do we add or subtract it?
Add.
Very good. We add it because a negative effect would be adding to that minimization problem. We get it. Let's try another. Constraint 3 says we only have 2 of whatever this is. There's only 2. And we finally get to where everything's being dropped off by our suppliers and only 1 gets dropped off. There's not 2. Yeah. First of all, is the dual price still valid for constraint 3, yes or no?
Yes.
Yes.
Because it's within the lower limit, correct? Now we look at the dual price on constraint 3, and it happens to be a negative $4.50. Okay. I want to make sure everybody's looking at me. You ready? I just gave you the constraints right-hand side for 3 was going down, not up. Think about this. It's going down. These dual prices are always telling you the effect it's going to have if it goes up. But you got to look at this and go, wait a minute, this right-hand side is going down 1 unit, not up. So you're going to say, this is telling me it's going to have a negative effect of $4.50 for every unit it goes up. But because it's going down, you got to say to yourself, it's going to have the opposite effect. Instead of negative, it's going to be a positive effect. Now you got to decide whether you add or subtract. This is a minimization problem. It went down instead of up. Negative effect if it had gone up, but it's going down, so a positive effect. Minimization problem, add or subtract.
Subtract.
All right, you're all happy because you think you got it and you're with me right now. But trust me, tonight you could have someone quiz you on this and you will forget this. There's the logic involved, and this is what you're going to accidentally do. This went down 1 unit, negative 4.5. Let's subtract it. Only because it's a negative, you're going to go subtract. Instead, you've got to go back and say, wait a minute, I don't know whether I subtract or not. This is just telling me the kind of effect, not whether I subtract or add. I have to say, wait, this is going down, negative effect if it went up, so it's got to have a positive effect. Then you've got to say, well, what does positive effect mean to that 27 at the top? If it's a max, a positive effect would be adding. If it's min, a positive effect would be subtracting. And that's how you got to interpret these changes. And that's what this chapter is all about, is taking the raw data from this output, and all these outputs have exactly the same data, but they display it in different ways every time. We're going to jump to one now from the book just because I want you to see slightly different output now.
So we're not actually calculating the dual price?
129 at random. Sorry, go ahead.
We're not actually calculating the dual price?
No.
That's going to be given to us?
Always. I am going to show you a calculation if we have enough time, but I don't know. What you need to do. Okay, I just randomly picked this. Are you ready? Our supplier, hang on a minute. I want to make sure you guys are with me. Hang on. Look at how it's worded differently. And I know I showed you this last week, but I'm sure you forgot about how the words are different on this. Even though it's telling you the exact same stuff, let's see if you can interpret it. Are you ready? Our supplier, which is represented by constraint 1, dropped off 20,000 less units. Wait a minute. I'm sorry. 20,000 more units than we expected. Everybody hear that? Let me say it again. Constraint 1 is represented by our supplier, who's supplying this raw material, and it dropped off. I'm purposely not giving you too much information because I want to see if you really get this. It dropped off 20,000 less units. Is the dual price for constraint 1 still valid? Yes or no?
Yes.
No. You said 20,000 less, right?
Yes.
No.
How did you interpret that? Anybody? I don't know the answers. I gotta look. I said more, didn't I? More.
You said both.
You
I
said
said
both.
less than I said more.
What do you want?
So if it's 20,000
More,
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 good.
more.
20,000 less,
Let's
we're
stop. Here we go. Ready? Constraint 1 is represented by supplier 1. Supplier 1 is represented by constraint 1. It dropped off 20,000 more units than we expected.
Yeah.
Okay, is the dual price still valid?
Yeah.
Yes.
Yes or no? I hear a lot of yeses. Any no's that want to jump in? Okay, I think yes also. But what did you look at? What number did you look at? Allowable increase. Yeah, that's the title of it. You're right. Allowable increase. This is not telling you how much it could go up to. It's telling you how much it could increase. And I gave you the question on how much it's increased, right? So I gave it to you as 20,000 units more than we expected. This is telling you how much more than expected it could go up to, and the dual price is still valid. 60,000. Because I'm only increasing by 20,000, 80,000 is the current value. And I didn't say that on purpose because I wanted to see if anybody thought this was the current value here in the middle, when they shifted over to the left side on this software output. It's currently at 80,000. 20,000 takes it to 100, but it could go all the way to 140 if you add 60 to it, and still the dual price would still be valid. Let's talk about the dual price now. The dual price for constraint 1 is still valid. Will that increase of 20,000 units have a positive or negative effect on our objective function value? Oh, no, come on, I wanted that. Positive or negative effect?
Positive.
Boy, I have answers. Oh, hang on, here we go. My question to you is, does the dual value, represent what would happen if the right-hand side goes up or down? Up. What's happening to our 80,000? Going up or down? Up. Will the effect for constraint 1 going up 20,000 units have a positive or negative effect?
Positive.
That's right, because it's a positive number. Matter of fact, these are all positive, so they would have to go down to have a negative effect. If they're going up, they're all going to have a positive effect. A positive effect of about 9 1/3 cents per unit up. How many units is it going up? 20,000 times 9 1/3 pennies. This is a minimization problem. Added or subtracted to 8,400?
Subtracted.
Very good. Positive effect would be a subtracted. 20,000 times 9 1/3 cents subtracted from that number is the new objective function value. Being able to understand that because this is going up, that this would have a positive effect. Then you looked up to see what the objective function was. You saw it was a minimize, and you said positive effect on a minimize would be subtracting. And I've had students in the past that literally set up a chart that says positive effect, minimize, subtract. Negative effect, minimize, add. You know, so they could quickly remember to follow which direction they should go in based on the logic that we've been talking about. That's what happens. The logic is forgotten. And then it's all, then students will say, oh, it's a positive, I'm going to add. It's a negative, I'm going to subtract. Without realizing, you really got to say, wait a minute, is this a minimize or a max? Okay, I think we're ready to put it all together in a story. Are you ready? I got to make sure. Okay, we haven't gotten here yet. We're still right up here. This is where we're heading before the end of today, I hope. Make sure you sign in the sign-in sheet. I know what's going on. Let's go to the first one. Yeah, let's go to the place. Yeah, let's do it. Okay. Oh. Go to the second. Okay, this bike. Oh, you guys say something. This bike company, they have these new lightweight bike frames they're going to manufacture, deluxe and professional. They're made of special aluminum and steel alloys, right? You guys put your mind in the mind frame. You're working at this company. It's a bike manufacturing company. We got these 2 frames, deluxe and professional. There's aluminum involved and steel. Different amounts of aluminum and steel in each of these 2 frames. The anticipated profits are $10 per unit of deluxe, $15 per professional. Where do you think this is heading? A max or a min problem? Yeah, we're giving usually when we're given the profit, kind of gives it away a little bit. That's probably we're probably going to try to max the profit. It says the number of pounds of alloys that we receive for this cycle of scheduling of production. On the next slide. Looks like we got 100 pounds of aluminum, 80 pounds of steel. Let's jump into writing our constraints here. First of all, what letters you want to use, what variables you want to use for, we're obviously trying to determine how many, what are they called, deluxe and professional frames. The D and P. So we'll go with the D, we'll go with the P. First one is 100 pounds of aluminum. Less than equal to 100 pounds. This is aluminum. I just put a long loop. We can't go over 100 pounds. That's all the supplier dropped off. Now we got to say, we got to connect these variables to this 100 pounds of aluminum in the form of a constraint by figuring out how much aluminum, this is how many deluxe frames we're going to build, but how much aluminum does each frame use. And that's in the chart right there. The deluxe frame uses 2 units of aluminum times however many deluxe frames we're scheduling, plus 3 units of aluminum on the professional frame, however many we schedule there. When you add them together, we can't go over 100. That's all we have from the supplier.
No.
I'm sorry?
4.
I showed this one before. What do you mean?
It should be 4, not 3.
It should be D2
sorry.
plus
I'm
D.
going to cross this field, didn't I? Thank you. Dang it. Thank you. 4. That's an easy mistake. Steel. How much steel did we get? 80 pounds. How much steel, when we do production, will be used by each of these bikes? Deluxe is going to use 3 units of steel. Professional uses 2 units of steel. Right? However many deluxes we're making, however many professional frames we're making, This is the amount of steel they'll use. We got 80 pounds of steel. What's the objective function? Let's go back here. How much? We're going to make $10 profit for every deluxe, so $10 times D, plus we're going to make $15 profit for every professional. You guys told me this is a max. Only 2 constraints. Can't believe it. There's our objective function. The question is, how many deluxe and professional frames should you produce in production for this cycle based on these raw materials? This is a very common, by the way. And you should. The other constraints would be, usually there's only so many hours in certain departments available based on somebody's on leave or whatever the case may be. So you got to figure out how many hours are needed in that department for the deluxe, how many hours are needed in that department for the professional. Then there's another department. There's only so many hours available. All right? So that's where we're headed. You're going to have 4 or 5 of these constraints. How many hours available, how much raw material, all of this is combined. So we write it up, looks like this, max, da-da-da. We never have to write this. We're assuming it the whole semester that our decision variables are positive. We're using D and P instead of X1, X2. That's the only difference. Same thing. We go ahead and put it into the software. Here we go. Linear programming, right? There we go. New. How many decision variables? How many constraints? Max? Okay. I'm going to change this to, we used a D and we used a P, right? The numbers with the objective function are 10 and 15. 10, 15. Everybody see how I'm doing this? The number in the constraint is a 2, then a 4. Is this a less than? Don't forget the equal is assumed. You only have to put a less than. And the right-hand side is 100 pounds. The steel is a 3 and a 2. It's a less than. And this is how many pounds? Thank you. We hit solution. We hit solve. There's our output. Are you ready? You're working in accounting majors. Your accounts payable person, because that's who does your buying also, your small office. That's who this supplier's been dealing with. They just got a hold of that person in your office, said, hey, I know we just dropped off 100 pounds of aluminum. Is that aluminum or steel? Aluminum. But we've got an extra 10 pounds. Do you want it? Yes, sir. First question is, will this extra 10 pounds affect the dual price?
No.
So the dual price is still valid. Takes us from 100 to 110, the upper limit is 160. Very good. Your answer's got to state, got to show that you looked at the upper limit. And you said the additional 10 pounds is within the upper limit, dual price is still valid. You've got to show that you looked and checked. Next, look at the dual price for constraint 1. Should what's happening, these extra 10 pounds, will it end up having a positive or negative effect?
Positive.
Positive. Because it's increasing, this dual price always tells you the effect it's going to have if the right-hand side of that constraint's increasing. Get it? That's what it's always stating no matter what. So, this 100 is going to 110. It's going to have $3, 12.5 cents positive effect, and it's a max problem, and the objective function value is representing the most profit we can get. So it's going to increase our profit by $3, 12.5 cents for every unit. We multiply it times 10. Do we add or subtract it to the $412.50, the maximum profit we're going to get from these limitations? Do we add or subtract it? That's right. The positive effect, because it's a max, would be added. So you show $412.50 plus $31.25, right? 10 units. So I multiply times 10. So instead of $3, $31.25. Your new objective function value. I want to make sure you know where that objective function value. When you were graphing, you went to the objective function and you placed in each variable what the optimal solution was. And that's exactly where that 412.50, and here, it's right here. D and P are our variables. The optimal solution is, we're supposed to make 15 of the deluxe bike and 17 and a half, right, manufacturing in process for the following cycle, 17, yes, we can make a half a frame, and a half professional, right? For this cycle. We'll have a half a frame, the next load of material just arrived. We're scheduling that half a frame to continue on with the additional materials. We multiply that times the objective function value, which is the profit we can receive. 10 times corresponding, 15 of them is 150. 15 times 17 and a half of those is whatever that equals. You add it to the 150, you'll get 412.50. And that's how that's calculated. Now the reason this is important, are you ready? We just found out, based on the supplier, that our cost is going to be a little lower than we projected. So our profit's going to go up a little bit on the deluxe bike. It's going from $10 to $11 per deluxe bike. Is the optimal solution that we already started production with still valid, or do we need to stop production and make changes? Let me say it again. It went from $10 to $11.
Still valid.
Still valid? Let production keep going, and we'll work it out ourselves, right? So we can let them keep going. You looked right here. It's currently at 10. It's going up to 11, and this one's showing you the upper limit instead of how much it could go up. So it could go all the way up to $11.50. So $1 obviously is not going to change the optimal solution. Now, you haven't been taught this yet. You ready? Anytime the objective function number changes, it will also change the objective function value up top. Because this was 10 times 15, 15 times 17.5. This is going up $1. So now it's 11 times 15 plus 15 times 17.5. Or if you're really fat, want to do it fast, this went up $1. $1 times the corresponding optimal value of 15 would be $15. Because that's going up, the objective function would go up $15. And that would be the quick way to figure it out. So you could take the change times the optimal solution for the corresponding change, and either add or subtract it, or calculate the whole new objective function value by taking the new number 11 times the optimal solution for that variable, and take this number times the optimal solution, add them together, and you get your new objective function value. All right, I want to make sure you got this. The profit for the professional is going down to $13. Is the optimal solution still valid?
Yes.
Because it could go all the way down to what?
6 and 2.
Very good. Very good. Now, will the objective function value go up or down?
Down.
Down. That's right. Because if this is going from 15, I forgot what I said to you. 13. It's now going to be 13 times the 17.5, 10 times the 15. So that's going down $2. 2 times the 17.5 is the amount the objective function value will be decreased. You could just subtract that or calculate the whole new objective function value. 13 times 17.5, 10 times 15, add them together, it will be a lower number than the 412.50. You get it? I want to make sure I point out what I did. These changes get multiplied times the optimal solution to figure out the new objective function value. These changes can multiply times the dual prices to figure out the new objective function value. And if you are in a hurry, one of these changes, somebody's going to multiply times the optimal solution and figure out the new objective function value, when it's only, you only do that if this were changing. So, range of optimality changes, you use the optimal solution to figure out the new objective function value. Range of feasibility, you use the dual prices to figure out the new objective function value. Everybody get it? So that's another thing you got to remember. All right, how are we doing on time? We got time? Doing okay? All right, here we go. Simultaneous changes. More than one change taken at the same time, which is more real life. Too much? Man, wish everybody could see the reaction with video. You need a break. You ready? The profit on the deluxe bike and the professional bike are both changing. The deluxe is going from $10 to $9, and the professional is going from 15 to 14. To make it easier, I'm going one change downward for each one of them. Now, you have to indicate in your answer that you checked the limits of each of those two changes to see if they're within their limits, one at a time. The 10's going down to 9, going down $1. Is it within its limit?
Yes.
Okay, so that alone's okay, right? Okay. The 15's going down to 14. That alone, is it within its limit?
Yes.
Okay, so that's okay. If either of those changes were outside the limits, your answer would be that particular change, whichever one it is outside of the range of its limits, and the optimal, we're talking about this, the optimal solution's no longer valid, and this problem needs to be recalculated. That's your whole answer, but I've had students give that answer, and it wasn't outside the range, and you didn't do all that work, and that's way too many points to lose. So you got to make sure, if you're given the answer, it's outside the range and the optimal solution is no longer valid, I would be safe and just calculate a new objective function value just in case you're making a mistake. Because that's a lot of points to lose if it really wasn't outside the range. You got it? Okay, we're talking about this right now, and there were two changes. You just got done telling me both changes are within the ranges. So right away, you want to go ahead and calculate the new objective function value based on these new numbers, which would be easy. I said this 10's going to 9. So instead of 10 times 15, 9 times 15. The 15's going to 14. So instead of 15 times 17 and a half, 14 times 17 and a half. And there's your new objective function value, or those who want it the fast way, this is going down 1 times 15, subtract it. This is going down 1 times 17 and a half, subtract it. Same answer. Got it so far? Do not do that until you figure out the 100% rule. So I don't know where you can write this, but anytime there's more than one change, you must do the 100% rule before you calculate that new objective function value. Don't let your instincts take over and you just start calculating the new objective function value. Because if it doesn't fit the 100% rule, there was no reason to do the new objective function value.
Say it one more time.
You ready? Anytime there's more than one change taking place, you must calculate the 100% rule, which I'm about to teach you now, before you calculate a new objective function value. Yeah, we've been talking so much this screensaver. All right? This is only when there's more than one change taking place in the same area. More than one change taking place with the objective function numbers called the range of optimality. Or if there's more than one change taking place in the range of feasibilities, which is the right-hand side of the constraints, right? Now I'm going to repeat what I just said, but I'm going to talk about the range of feasibilities again. Ready? Anytime there's more than one change taking place simultaneously in the right-hand side of the constraints, you must calculate the 100% rule before you determine whether these dual prices are still valid or not. Just because each change is within its upper or lower limits still does not mean those dual prices are valid. When there's more than one change, the determination is truly whether it fits the 100% rule. Then you can say whether the dual prices are still valid. You ready for the 100% rule? It's not that hard, but you've got the hardest part to remember to do it. That's the hardest part. It's really what we're calculating is that we're going back up here to the objective function. I said the 10's going down to 9, correct? And I said 15's going to 14, correct? As long as you add up the percent of change that's taking place compared to the amount that could, you know what? You guys are going to miss this. You ready? The 100% rule says, I want to make sure you get this. You got to calculate what percent of the change that's taking place compared to the amount that could take place for each change. Add those percentages together, and as long as they equal 100% or less, everything's still good, and you can get the new objective function value. If they add up to more than 100%, that's the same as being outside the ranges. And either the optimal solution or the dual prices, depending on which one you're evaluating, no longer valid, and this whole problem has to be redone. And that's your answer. That this is over and above 100%. You ready? We're going to do this one right here. 10 going down to 9. here's the part where everybody goes, what are you talking about? You ready? The 10 is going down to 9. My question for you is, how many unit change is that? 1. Over. How many unit change could have taken place? Now I want to add this, in the direction the actual change is taking place. Did anybody hear that? Is the change going up or down?
Down.
Only compare it to the amount it could have went down. Somebody in this room is going to compare it to the full amount it could have changed. This whole range. Only the amount it could have changed in the direction the change is taking place. So how many units could it have gone down? How many? Looks like 2.5. Does that sound right? Let me make sure everybody sees where I got this. 10 is going down to 9. It could have went all the way to 7.5. If you do the math on that, that's 2.5 units. It's going to do 1 unit over 2.5. Give me some math on that. That's 40-something percent. How much?
40%.
40 equals 0.4. Doing the next one now. 15 is going to 14. How many unit change? 1 over how many units could it have changed in the same direction? Come on. How many? 8 point, is that what it is? 3333 probably?
Yeah.
What we're doing is we're saying 15 is going down to 14. So that direction, which is down, could have went all the way to 6.67. 15 to 7 is 8 units, and then you get that 0.33. So this is 1 over 8.33333, which is a very small percent. 0.16, someone give me some. 0.12?
Yeah, 0.12.
0.12? 0.12, is that sound right, or 0.2? 0.12. Now we add them up. 40% plus 12% is 52%, or 0.52, which is, you gotta show me you compared it to 100%, which is less than 100%, or 0.52 is less than 1. You wanna turn it into decimals, which means we're right here, right? That 15 and 17.5, still valid. And we can calculate the new objective function value. All right, because we're under the 100%.
So does that mean it can be less than or equal to 100%?
Yes, or equal.
Okay.
As long as it's less than or equal to 100%, then this is still valid, we can calculate. If we would have added these, and we went over 100%, you know, the simultaneous changes have taken us over the 100% rule, and the optimal solution, because we're talking about optimality, the optimal solution is no longer valid. And we would have to recalculate this whole problem, which is a big deal in real life because you have multiple variables, you have multiple constraints, and redoing the whole problem is going to take some time. And now, if this is a real problem on a quiz, you show me that these two changes are within the 100% rule, and now it's going to say, and if the optimal solution is still valid, what would be the new objective function value? And you've got to calculate it. Well, this went down 1. 1 times 15, there's $15, subtract it from 412.50. This one's going down 1. It's being multiplied by 17.5, so subtract 17.5 now. And there's your new objective function value. Or 9 instead of 10 times 15 plus 14 times 17.5. Add them together, you get the same answer. There's your new objective function value. You have to, don't bypass that last part. Matter of fact, most of you will calculate a new objective function value. This is what gets skipped the most. And believe it or not, there's a lot of points here. You're looking at 4 points on a 6-point problem. There's 4 of it on this 100% rule. That's the whole point of that problem, is that you're able to recognize there's more than one change taking place at the same time. That means you've got to do the 100% rule. That's the whole point of the problem, that recognizing that there's simultaneous changes. You ready? We're going to do another one. This time we're using right-hand side. What? So, thought maybe I forgot something.
Optimality and feasibility, that's all they're going. That's not.
No, they're separate. What we just did was optimality. If there's simultaneous changes taking place in the objective function numbers, if there's one here and one here, you'll never get a problem like that. Those are not simultaneous changes because they're completely different things. Simultaneous changes in the same area. Optimality or feasibility. So constraints or objective function. Simultaneous. So now we're going to have simultaneous changes on the right-hand side of constraints. This supplier said it's dropping off 100 pounds of aluminum. This supplier said 80 pounds of aluminum. The aluminum supplier only dropped off 90 pounds, but the steel supplier dropped off 90 pounds. Did everybody hear that? 90 pounds each. We're going right up here. 90 and 90. Are you ready? You tell me, someone, what's the first thing you're going to look for right now? If what?
Oh, yeah.
That's right. Exactly. Are each change within their limits.
Yes.
And you guys show me on paper that you write something that shows me that you look to see if they're in their limits. The first one's going from 100 down to 90. It could go down to, very good, 53.33. So 90 is within the lower limit. That's good. Go ahead.
We just write 90 is
Within
less than or equal to 53.33.
Well, it's greater than.
Or greater than.
Yes. Yeah, sure. That shows me you compared it. Yes. That's what I'm looking for. Whatever you write, and I don't care what it is, I just need to see you did make the comparison. That you checked it. Now the other change is going from 80 to 90. Is it within this limit?
Yes.
Which limit did you look at? The upper limit, which is? And it's going up to 90, so it's within its limit. So both are within their limits. That's the first step. And somewhere on there, you've got to show me that you compared both to their limits. Now, you've got to remember, we have more than one change taking place. I can't figure out the new objective function value until I figure out if it meets the 100% rule. This is the feasibility 100% rule. The math is the same, the logic is the same, but it's all about the right-hand side of the constraints and their limits now instead of here. And what you're checking is if these are still valid, not the optimal solution, you're now checking if these dual prices are valid with this change. You ready? The first one was the 100 going down to 90, which is a 10-unit change, but the 100 could go all the way down. You told me to 53.33, which is how many units? 54 would be 46 point.
667.
So this is 46.666. Does that sound right?
667.
Yeah, you do know. I got to write over this. Is that the same thing? Okay, I'm going to keep going. This 90 is going up 10, but it could go up how many units? This 80 is going to 90, which is up 10. It could go up how many units? 70. 10 divided by 70, that's only 0.7, right? Or help me out, 0.07? 0.20, 0.17? 0.21? Come on. Anything. 0.14 what?
0.14.
What's this one? 0.14. 10 divided by 46, that's 0.21? 22? 0.21. I add them together, 0.21 plus 0.14 is 0.35. It is less than or equal to 1.0, 100%, 35%, right? I just used decimals as all. Because 30.35 is less than or equal to 1.0, 100%, 35%, does that mean our optimal solution is still valid? Yes or no?
Yes.
That was a trick question. Let me say it again. That's right. We're not even checking the optimal solution. It's if the dual price is still valid. This isn't anything about the optimal solution. This is the right-hand side of the constraints. The question really is going to be, are the dual prices still valid? Yes or no?
Yes.
Yes, because we're less than 100%. Are you ready? Here's the weird part. One is going down, the other is going up. We'll look at the first constraint. That's the one going down. Its dual price says if it were going up, it would have a, what kind of effect?
Positive.
Positive effect of $3.12 for every unit it's going up, but it's going down. It's going down 10 units. So it's got to have what kind of effect?
Negative.
Negative effect. 10 units times $3.12 is $31.25. This is a maximization problem. Do we subtract or add it?
Subtract.
Negative effect would be subtracting. Now, let's do the other one. It's going from 80 to 90, up 10 units. The dual price says it's going to have a positive or negative effect if it goes up. Positive effect of $1.25 times 10 is $12.50. Add or subtract? Add. We first subtract, then we add. You've got your new objective function value. You see the steps though involved to get to that point, because that's what you're about to have on your in class and your homework on Thursday and your quiz a week from today. You're gonna have a problem, it's gonna have simultaneous changes. You gotta tell me, you gotta first show me that you looked at the upper and lower limits and said they're either in, within, or not. You gotta show me that you then did the 100% rule and determined whether either the optimal solution or the dual prices are valid. Then you gotta calculate the new objective function value if it is within the 100%. And I wanna tell you, even if you find a problem that's outside the range and you find a problem that is more than 100%, I would still maybe go ahead and calculate the new objective function value just to be safe. Because if you say, oh, the dual prices are no longer valid, this problem would have to be completely redone, and you didn't do all that work to get the new objective function value, how can I give you partial credit on something you didn't even attempt? So, because of you accidentally misinterpreting possibly.
We get marked down for doing actual work when it actually wasn't.
No. And don't ever erase work. If you did wrong work, don't erase it. Cross it out and do more work. Because if there's any points that I can give you for the work you crossed out that I can find right because you did it wrong even when you redid it, I'm going back to the work you crossed out. If you erase it, I can't find that work to give you points. I'm looking all of your work, no matter how sloppy it is, to give you as much partial credit as I can possibly give you. So never erase work. Cross it out and use the back of a page or something, because even wrong work can get you partial points. All right? I think that's enough for today. Let me just look.